I guess. So yeah, hello everyone. Welcome to Neural Network Architecture Selection Workshop. So previously, I think we did like optimization and just basic learning, gradient descent, and all that. So this is the things that we have done. Optimization, we did some regularization techniques. We talked about overfitting, underfitting, optimizers, atom, momentum. So now that we've like talked about optimization and how your models are learning, let's talk about like how would you structure your model, or how would you want the like model to look like. So this is what we are going to talk about, the layers that we are going to have, like why do we have what layer when we have it. Mostly there are like three different kind of layers that you can have: convolutional, recurrent, and LSTMs. And then we can like look at some code and have a live demo maybe. So this is like a basic convolutional neural network. And even if like right now, if you don't understand what all of these layers are or what they're doing, no worries. Yeah, no worries. What we can do is basically like we'll go through all of them: convolutional pooling, fully connected, and all that. So, but this is what a convolutional neural network looks like. So till now, what we have basically talked about is just fully connected new layers, which basically means if you have let's say 25 neurons in the first layer and 10 in the second one, then you'll have like 10 arrows going from one each of the, or 25 arrows from each of the ones in the 25 to the first one. So 25 into 10, you'll have like 250 weights. So sometimes they are not worthwhile, or they are like not okay. So that's why we have different kind of layers. So let's see them. So first of all, this is the one that I just talked about, fully connected layer, or a dense layer as we want to call it. It's mostly just like every input feed forwards to every output. And one big like red flag from this that you can see is there's just like so much computation to be done. If you have like a really big amount of input, then it's just like you have to compute a lot of output for that. So we need to reduce that. That would be the main problem. And these are the layers that we've been using all this time and the most common ones. So yeah, let's go next. So what are the dropout layers? So in this one, what we are doing is basically saying that, okay, some of these neurons are not going to feed forward at all. So we specify a probability in which each neuron in a level will be dropped. So let's say if you say the probability is 0.3, and then each neuron in this layer has a 0.3 or a 30% chance to not be considered for the next layer at all. And this would like help you with overfitting, because when you're like, when your model is way too complex, that means there's like way too much that you're learning it. It will help you rather to just overfit on the training data. Now you can like generalize it better. So let's go next. So the max pooling layer. So what this layer does is it will like it will obviously reduce parameters to learn, because it's going to take, we'll see this in action. We'll see like a demo of it, like how this actually works. Because I think with the pooling layer, it's much easier to visualize it. So we'll definitely see that it's like a n cross m rectangle, and then it outputs the max value because it's max pooling layer. There are different kinds of pooling layers too with it. And stride would tell you basically how do you have to move that rectangle, right? So those are the two main things of this pooling layer. And what translation invariance means that if you have something on the left, right? If you have something, if you have like a dog on the left side of your image, and then you like put it on the right side of your image, it's still a dog. Like it doesn't change the fact what it is. So that's why like this works. And also you can use like the locality, like usually like you can see it if there's blue in the like near the water, mostly like the pixels around it are also blue. So that's another thing, locality, that's you can think about it, like nearby pixels are usually of the same value. So let's do a 2x2 max pooling layer demo. So what 2x2 max pooling layer means is that you're going to choose from 5, 27, 12, and 130. So you have a 5, 27, 12, and 130. So in this one, you have a stride of 2. That means at each step or the next stride, you would move 2 pixels. So right now we did 5, 27, 12, and 130. In the next one, we're going to do 3, 9, 99, and 65. So that was the stride means. And what we are doing at each step is basically choosing the global, or not the global, but like the maximum. So 5, 27, 12, 130, we choose 130, 3, 9, 99, 65, we choose 99, we choose 109, we choose 54. So that's for max pooling layer. Now, obviously there are other kind of pooling layers too. So as you can see, like from the max pooling layer, we're just getting the max, and we like pretty much forget or don't consider the pixels around it. With average pooling, we would also be considering the pixels around it, and that's thereby like creates a smooth, or like smooths the input that we're going to feed forward. And global max pooling is just you take the whole entire grid and just choose the maximum value that you have. So average pooling 12, 22, 30 to 54, add them all and average them, it should be 30. All right, so which dropout layer do we use if we want the following action? So any guesses on this one? Think about it's you taking the max out of like all of them. So think about like, so you have like this input and this, you basically take one single global maximum. So that would be your global max pooling. Yeah, and if you were to use a max pool 2D, you won't have just like one output. And if you were to use like an average pool, again, you would have done, oh never mind. Yeah, if you had like an average, then you would have done the average things. So like 12, 22, 32, 54, you would have taken the average, and then have like for a 4x4, you would have like a 2x2. But in this one, since you take 4x4 and have a 1x1, oh, gotcha. Oh, network architecture. All right. So what do you do if like you have a 3x3 matrix and you cannot like with the stride, it's not working? So for that, what we do is we use padding. And the good thing about padding is that it just helps you with dimension mismatches. And there are no like corner cases or edges with that. Let me open the chat. All right. So we use like when you have dimension mismatches and like it's not working because the pooling layer is greater size, then you can like use padding. Padding basically would just add zeros all around it. And since it's average and maximum in both the things, your zeros won't affect anything since it's pixel values. So finally, till now, what we are seeing is, so X cross Y or like N cross M input. And usually like eventually like in your neural network, you would want one single layer, N comma 1 or something. So this is like what it's called flattening. And it's usually the last step after you've extracted the features from a convolutional neural network. So in this thing, you can see like 1, 1, 0, 4 to 1, 0 to 1, it's a 3x3. 3x3 becomes 1, 9, and you get 1, 1, 0, 4 to 1, 0 to 1. You can think of it as a input layer of 9 neurons. If you take that, it's still the same thing. And now you can like build a neural network of as you want it, fully connected, or dropout layers as you want it, using this 9-layer input. And a good example is 6, 6, 5, 1, 2. And when you flatten it, you get 18,432 output dimensions. Really helpful in reducing the amount. So pooling, all the pooling that you have done would help you like in reducing the amount of dimensions that you get at the end with the flattening. So we've been talking about convolutional neural networks. We've basically covered most of the part of it, except one, like the convolution layers itself. We've talked about pooling layers, we talked about flattening, we talked about dense layers, we talked about dropout layers. So let's talk about convolutional neural networks right now a little bit and see like how they are used. They're mostly used, like a high level idea for you would be just to think about like if you have an image and you mostly like want some features from that image. So what convolutional neural network would do is extract those features, and then it will like feed it forward to the neural network that's like connected to. So extracting the features, and then some classifier would be used to image classification or whatever you want to do. So let's see like what this convolution layer is doing, because that's probably the most important thing. So right now, as you can see, like the yellow thing that's like moving around, that's called like a kernel, and it's moving with, I think, the extra one. So the first 1,1 of that is 1. So it's like 101, 010, and 101 kernel that's like sliding around. And at each step, what it does is it multiplies whatever the kernel is to whatever the actual value is at that point and sums it up. So in the first block, if you see, and in the first kernel, if you would like multiply each value in the kernel with the value as the input, you would get like 4. So that's basically what this kernel and this is basically what a convolution layer is that you have a kernel and you use that kernel to from that image to get a convolved feature. And these kernels are basically like then learned. And the good thing about these kernels is, as you can see, there's only one kernel for the entire whatever the 5x5 layer input is. Your input could be like really big too, but even then your kernel would still be like 3x3 or whatever. And so you would have only one kernel for the entire layer, and that's really great because now you don't have like a fully connected layer or from like 1024 to something. So reduces the amount of weights that you have to train and makes it really helpful, and it's like really helpful in optimizing. So let's talk about like the architectures, I guess, a little bit. So now we've seen some architectures. This is VGG16. The one that's here, it's Con1, convolution 1 layer, convolution 1, 2. And most of them, that what they do is they'll have like convolution layers and max pooling layers, one after the other. So convolution layer, max pooling, convolution, max pooling. And most of the time, what the aim is to extract features and reduce the amount of input that you're going to feed forward to the final dense layers. Because again, with dense, the number of weights can shoot up really high. And the amount of computation that you have to do can go really high as well. So to reduce that and keep both to the minimum, we try to extract features. And again, like the high level idea is just extract features from the images, useful features, and only feed them forward, because otherwise it would blow up, or it would like blow, it would just take so much time because you have to do so much computation with the dense layers at the end. Oh, one more point is like we don't need to make our own feature extractors. Yeah, that's a good point, because they're already trained like for you. So what you can do is you can use VGG16, and at the end you can like remove the layers and like freeze the layers, I think, as they call it. So you can like remove the layers at the end and make your own and use your own classifiers from that. So you can basically use a pre-trained model which extracts features and then use those features to classify or do whatever, or for classification. And that's like, I think that's also called transfer learning. And it's really useful because now you don't have to train the kernels that, like, as I said, you have to train kernels with convolution layers. If you use VGG16, Resnet, or whatever, like AlexNet or whatever, but at that point, you won't have to train the kernels. So really helpful, reduces the amount of, again, with convolutions, two things that I would want everyone to take away is it reduces the amount of input and it extracts the features that we want so that we can then use these features and this reduced amount of input in the dense layers for our main classification, because that's like our goal. And this is like region propose ROI. So basically, this one I'm like not exactly sure. Uh, so region propose, skip this one. So this one I'll like go back to it. I'm not exactly sure about this one. Should I just delete the slide, I guess. My bad. So let's come back to this point. How do convolution layers differ from pooling layers? So let's like take a look at each of these points. So they take different dimensional input. Only convolutional only convolutional layers reduce size of input. They take different size kernels. All of the above, none of the above. Any guesses? All right. Just wait like 10 seconds more. All right. The answer is none of the above. So if you think about it, like how do they differ? A convolution layer and a pooling layer, like still taking the same size. Pooling layer also reduces and different size kernels. That's not different. So those that was the main thing about convolutional neural networks and convolutional layers. For most of it, two things is like with the convolutional layers, you have a kernel. Pooling layers, you also have a kernel. It's just the way that the kernel is like working, it's different. With convolution layers, those kernels can be trained so that the features that you extract to at the end to feed forward to your dense layers are like actually meaningful, because that's what you want. Because let's go back to this slide. So like on this slide, right? So what it's doing is it's trying to extract like the features of a boot that might be helpful for you to like actually realize, okay, this is like maybe the tip of the boot or the starting of the boot. So it's that's why like what you want to do is extract features from convolutional neural networks. Like that's what the layers do basically. All right. Till now, with fully connected layers. So like dense layers, you have uh we talked about dense layers, we talked about dropout, we talked about pooling, average pooling, max pooling, global pooling, and convolution layers. Till now, there's been no concept of say time. Like how do you know what's going forward? Like what was the previous input? And if your output is going to be dependent on like the previous, like a lot of previous input, then you have to like figure out a way to map time into your model. Like how does your model understand the concept of time basically? So that's where recurrent neural networks come in, really helpful for that. And let's talk about, so these are like some use cases. You can predict next word in a sentence, word generation, using like music generation, translation, image captioning. And image captioning is also like really good because you can use a convolutional neural network to extract features and then use that for your captioning. So it's one of the good things about it. And again, the dense layers and dropout remains the same. Back propagation remains the same. It's just a different kind of it, but the idea is still the same. And the way that is trained is also still the same. So let's talk about back propagation through time. So we've already talked about back propagation. If you're unfamiliar with it, just think about it as you have some difference in the last layer and you use that difference to calculate how much should the weights in the first layers should change. That's basically like a general idea. If you have a large difference, change them like a lot. If you have a very small difference, don't change them that much. Makes sense, because you're already like maybe close to optimal solution. So what's new with this one? So recurrent neural networks are like sequential, right? They go like this. And but previously you had like big layer, but now it's only one layer. So that's the difference. So let's talk about like one forward pass. So you had some random initialization at time step one. You output y1, time step two, y2, time step three, you output y3, time step four, you output y4. And this is the unrolled neural net. This is unrolled RNN, but if it was not, then the H1 is like basically going back to the neuron itself. So this is like a more unrolled kind of a thing. So let's talk about the loss now. So with loss, what's happening is that at each time step, you have to make sure, or you're like adding up the losses. So with each time step, the gradient is like, or like the loss is there. So let's talk about the main thing that's gonna happen. So now you're going to back propagate all these losses and differences. So let's say you had like a loss of like whatever, and so each time step you have to make sure that this loss, like this big difference, uh, is incorporated at time step 1 too. Maybe like you messed up in the time step 1, and that's why like you have a big loss. So you need to make sure that all of them gets updated according to the final difference that you have from the output. So suppose a sentence was how are you, and you like totally misjudge it and like I am them or something. So then like your time step 1, your time step 2, your time step 3, like all of them are just totally incorrect. So how would you then back propagate, right? Since it's only H1 feeding itself. So here's the problems that arises with something like that when you completely misjudge the output to the input, or like you completely are just predicting some random stuff. So so what happens is like exploding gradients. So when you have like sequences, you have time steps, and you have to back propagate through each time step. Now, if you have like a lot of difference at each time steps, what's going to happen? Like towards the end, your gradients are just going to be way, way, way big. And that's one thing that you cannot have, because you cannot have gradients that are exponentially large with respect to the time. And another thing is you can have like gradient vanishing gradients, exploding gradients and vanishing gradients. Both the problems exist. So you cannot have vanishing gradients either. That basically means something small exponent to the time. So another thing that won't work. And also you can think that, okay, if you're having time steps and you have to do it again and again, then the computation is just going to be higher too. So you need to take two of these things into consideration, and taking them into consideration, it turns out that RNNs are simple RNNs are not actually really worthwhile, or doesn't, they do work really well. They do work really well, but there could be something better. So enters LSTM, or long short term memory. So what this does is it fixes the issue that of exploding gradients with RNNs, and it has a special cell with multiple calculations. It contains 3 gates. So let's just talk about the diagram a little bit. So you see there are like 2 black arrows passing through. These 2 black arrows are considered the cell state. And what these 2 arrows does is you can think of them, what I like to think of them as like conveyor belts. And at each point, like each LSTM or like has an option to either forget to read, forget or write. So let's say like the gender of the person that was in the subject is something else, and now not like now it changed. So from the cell state, the LSTM at, let's say, time step 1 and at LSTM at time step 11 or 12 would time step 11 or 12 would basically change that information. And that's kind of like the main idea, is that you have 2 cell states, they keep running and they keep going around, and your LSTM has the option to either write, read, or forget. And what these like tan h, x plus, and all those does is, I think they're like the dot-wise operators. I'm not like the math, I'm not so sure about the math behind them, the exact formulas, but the general high level idea remains the same. Right? So yeah, forget, get. No. Yeah, they are just activation functions. Yeah, you're right. So they basically say yes or no if you want this or you don't want this. If you want to write it or you don't want to write it. So yes or no. Oh. So yeah, for get sigmoid output value between 0 and 1. And you're going to just use that to further away from the current version of less influence. Yeah. Main idea is still there's one cell state, so now you don't have like that problem of vanishing gradients where you have to compute gradients at every time, and just like that makes it much easier. No exploding gradients, no vanishing gradients, computationally much better. So as you can see, like LSTMs are a better version of RNNs, and like convnets would help you in extracting features from images, and fully connected layers are just, I guess they're just fully connected layers. There's not much to it. Yeah, these are like all the layers that you have: autoencoders, variational autoencoders, sparse, Markov chain. There are like a lot of them. I think we talked about perceptron. You can think of it as like a yes no. We talked about feed forward, deep feed forward. Just add a lot of layers to feed forward, becomes deep feed forward. RNNs, LSTMs. Oh, perceptrons were covered in workshop 1. All right. Yeah, that's great then. Yeah, any questions about like layers or anything? Let me open the chat. Some common conventions when designing a neural network. For that, I would say depends. I would say a lot of it depends on your input. Oh, like for image classification, at this point, what I would do if I was to do image classification is take some already pre-existing good model, like a Resnet 50 or VGG something, and then at the end, I would, when I've like, done the extraction, at that point, I would just use my own layers as I want them. So in terms of like conventions when designing a neural network, like specifically for image classification, I think you would generally just use a convolutional neural network. And otherwise, like it depends on the task as well as like what you want to do. If you have a simple data that you want to predict something from, then I don't see why you won't just use a simple deep neural network. But suppose your task is to do like text generation, music generation, something in which the current output depends on the previous input. At that point, you would use something which has some sort of time memory. Like it can like store details about time. So that's when like you would use RNNs, LSTMs, or any other thing for that. The previous bot, does the CNN also be best? Is the CNN best for facial recognition? I for facial recognition, I know the ones that like did in Python, you can basically like use a har classifier or something, and with like if you run it, it's a small script. If you run it, it would like open up your webcam and it would like put a square around your face. And what it's doing is basically, as you can see, like your eyes, right? Your eyes are usually like the same way, and also like the eyelids, they are mostly the same thing, and they kind of like really differ from, let's say, like just your face. So I think they use CNN for that only, but I cannot say that with 100% surety, but I'm pretty sure they use, but they're not the most. Yeah, I'm not, I haven't done like anyone else, like Stone, have you, can you?
What's the question? It's about facial recognition.
Yeah, it's about like, which CNN would also be, like which CNN would be best for facial recognition?
There's a lot you can do in computer vision. In addition to just plugging in a CNN model, what often happens that I've seen. So Snapchat uses some more old school tech, like manual features and patterns. What happens is that you also need to do some extra feature engineering. So not instead of just feeding a picture of a face, you would like to also do some extra engineering. So what I've seen happen before is, well, I don't know the exact mathematics for the computer vision stuff, but you can generate different kinds of feature maps, not using CNNs. So let's say, here's a very classical example for edge detection. You use what's called an edge filter. You apply a convolutional filter, and this filter is what's called as a Sobel operator. You can search this up. Once you detect edges, this helps you generate a feature that normally would have to be learned in a convolutional neural network. For example, if we're looking to trying to recognize someone's face, their facial shape is one thing. Another thing is like maybe the hair or something. That's super explicit things. And I'll call these explicit things like priors or conditionals. If you add any kind of useful prior that has low noise but high signal, for example, like your face shape is generally like pretty good. That always helps improve your model. But in the end, you end up just feeding that into a giant neural network. But yeah, there's additional annotation features you can add in instead of just a raw image. Yeah, there's a lot of things in computer vision that require further annotation instead of just feeding the wrong thing. Like for example, one thing is like speed estimation, or basically looking at what's called optical flow. So let's say you're looking at a static image or maybe a couple images, right? And you want to estimate the speed of the person in there. Or actually, no, let's say you're looking at a video. You want to estimate the speed of objects in there. The classical solution is what's known as optical flow. You can search this online. Just two kinds. It's called sparse optical flow and dense optical flow. These basically generate like flow vectors that tell you the direction they're moving in and approximately the speed they're moving in. Well, this is one way of getting speed, but it's not necessarily accurate, and it's missing a lot of information. So usually what happens is in these kind of convolutional neural networks, or even 3D ones, where they use what's called point cloud data, they'll feed in this flow information in addition to the image itself. And with speed estimation, they also have some kind of LTCM kind of architecture to encode speed. But yeah, there's a lot of different things you can do when designing things. One of the most common things I've seen is basically how you design certain priors in it. Priors being like things you know should be true. Like for example, when you're identifying something, you have to look for this feature. And the point of that is just to make training easier, and also potentially increase the upper limit of your model's ability.
Yeah, I'll post the slides on the Discord. So make sure you're on the Discord. All right. Here's some basically some links for you to go through. Yeah, that's it for the code. We could go through the code, but we haven't like tried running it or anything. I could like just talk about in general. So like I guess for most of the part, like with this like neural networks and stuff, is like you decide what images, like what layers you have to use, right? So if you know what layers you have to use, at that point it's just reading the documentation on how to add layers. So as much as like the code is important, I would say focusing more on the high level ideas and like why do you want to use a convolution layer here, it would be much more important. So the code really doesn't like do much in terms of like choosing the layers for you. You choose the layers for yourself. So basically, but you have layers. I think this is Keras. So Keras, in the Keras documentation, you have convolution. So 2 convolutional layers, then a max pooling layer, then an average pooling layer, then a global max pooling layer. And then finally, after you've like extracted the features, there's going to be one flattening layer, a dropout layer, and then finally a dense layer. So these dropout and dense layers are basically those two ones that we talked about in the beginning, and we also have like the convolution ones. And for the RNNs, same thing. You have sequential. You have one LSTM layer which contains 128 units. Then you have a dense layer. So only one LSTM layer. You can have multiple of them. Usually, I think like one LSTM with dropout, then another LSTM with dropout would be really good. And like most of the time, 2 or 3 LSTM layers would do the job, and honestly would be overkill. So yeah. So for the coding part of it, most of it is just like choose your own layers after you've decided which layer you want in your neural network. Just search Keras layer, Keras dot layer or something, and it will like give you that documentation. So you can use that. And that would be it. Yeah, and that's it. If you all have like any other questions, I'm gonna stop the recording right now. Thank you for coming. If you're watching this video, then thank you for watching.